So welcome back. We are coming back into the room and to follow the second part of the deep learning for computer vision. So Anthony and Silvio.
Yeah.
That's great.
Right. So I hope you still have some energy for the next hour and a half. Now we're going to talk about some concept of deep learning applied to computer vision. Before we talked about just the computer vision itself, what's an image, what are the different tasks, what is the different input, output, and different problems that we're trying to solve in computer vision. We talked about deep learning, what the neural networks look like, what the neurons look like, what a deep neural network look like, how the training of these deep neural networks look like. And now we're talking about the specific application of deep learning for computer vision. So deep learning with images is a bit different than it is from any type of input data that you might have. The single fact that if you take a high-res image, full HD of that tiger, for instance, if you take every single pixels and they have 3 value of RGB, that number of inputs is already 6 millions. And 6 million input variables, if you have understood that we have a neural net, a single layer would actually take those 6 million input, and I want to map that into 100 values, I would already have 600 million parameters to fine tune, just for the first layers. And typically you can go like up to 100, sometimes 1,000 layers. So it's definitely not optimal to flatten the image like I told you how to do before. So we do not flatten images on computer vision. So why is that inefficient? The image data actually has a structure, and that structure is extremely important. It's what defines an image. It's a two-dimensional matrix that is either 1 or 3 channels, which is the gray images of the RGB, sometimes K channels if we are multispectral. But it has a structure. It has a number of pixels. It has a huge dimensionality, but it has a structure itself. And in particular, if we look at an image of that cat, for instance, the single color of the pixel does not tell any information about whether it's a cat or not. It just tells you a pixel is black or a pixel is actually white or pink or so on and so forth. So actually, it's what the spatial correlation between these pixels actually tells us some information. The fact that the black pixels of the eyes, the center of the eyes, with the brighter pixel of the white part of the eye is actually together, that defines an eye, for instance, but it's not like the single value. So the way we tackle image is through convolutional neural network. And what does a convolution look like on an image? Instead of actually flattening that image, and there is like very low correlations maybe between one pixel on the top left with the bottom right, or like a special contribution of one specific pixel. Instead of taking an image like this and flattening, what we typically do, we create patches. We create tiles of smaller images that together compose the image, and in their singularity, kind of like understand what inside that specific tile is about. So typically, we break the image into overlapping tiles. So they might overlap those tiles. And we just process the tiles with a smaller neural network that has a way smaller number of parameters than the 6 million that I just told you before. Typically, the input tiles could be 3x3 images, 3x3 tile, or 5x5s, or 7x7, just to give you a range of how big are those tiles. And we learn a very small neural network, which has a way lower number of parameters, that will process every single input tiles and provide you with the output that you're expecting for that specific locations on the image. Then we store these results into a new array, a new matrix, and basically we go from these tiles. We have a small neural network that is applied for all those specific small tiles that are shared weights. Shared weight means every single tile takes the same neural networks to be processed, and it provides you with an arrays of a matrix of vectors that gives you some information about that. And the spatial structure is actually preserved such that the neighboring features the vectors that you have, in those like yellow dots, are quite related to each other if they are one next to another. There is different like application modules or blocks that actually define the convolution neural network. One of them is also downsampling. So if I take the original input image that has been processed and create like some features that are still have a spatial structure, I have some operation of downsampling, for instance, that I take the maximum value, max pool, that basically reduce the learning, the dimensionality, spatial dimensionality to something a bit smaller. Typically, like a full convolutional neural network pipeline is nothing else than the convolutional neural network that I just mentioned here with like these convolution operations, some max pooling that happens at the level of every single layers. You can have like multi-level layers of convolution max pool, convolution max pool, and then at the end you finally flatten again, not the pixels themselves at a very high resolution, but in a very smaller resolution like this one, you can flatten that that features and learn a fully connected neural network that would just have the scope of classifying those features. So if we in the representations that Anthony introduced, where we have features being extracted and then a classifier learning how to classify this part, the convolutional part until the max pooling part will be a way to extract features in a very efficient way to have a representation of that image that is extracted with way lower number of parameters due to the fact that we have a shared weight for that small neural network. And then we have the classifier, which is nothing other than the fully connected layers, taking this data and just giving you the likelihood of it is A, it is B, and so on and so forth. And the more, yeah, that's exactly what I was explaining. So the input is RGB image. In that case, something that looks like a car. You would have multiple convolutional steps with also an activation layers, of course, some pooling layers that will just reduce the dimensionality, some other convolution, some other pooling, and so on and so forth, until you reach intermediate representation that you flatten. You don't flatten the pixels that could be millions of entries, but something that has a range of maybe thousands of features that would describe what that image is. And that's the feature representations that nowadays is also trained in a self-supervised fashion. So basically a way to extract generic features or fully supervised features that describe your input. And then these features here is classified in a fully connected layers. It's the exact same way I taught you with a neural network, deep neural network I told you, where we have fully connected layers that get activated with a softmax to tell you whether it's a car, a truck, a van, a bicycle, and so on and so forth. So that idea of convolutions is actually not something that is new. It comes from the literature of computer vision. Computer vision is more than just deep learning. Deep learning has been introduced maybe 10, 15 years ago in computer vision, but computer vision is like 30 or 50 years old so far. The concept, some concept that was being introduced in computer vision is the concept of filters. Filters will be an operations that you can do on specific image, like on that specific image on the left. If I do a convolutions, which is basically multiplying a feature, your image input with a specific filter, you would actually activate some specific part of the image. So we can't see much in here, but this is like typical 5 filters that are being handcrafted over the last decades to highlight part of the image. In particular, for instance, in the first 2 one or the 3 one, we have some filters that focus more on the edges. So this is like a very common filter, it's called the Laplacian filter, as far as I remember, that activates wherever you have an edge and high gradients between neighboring pixels, and basically highlight the contour of an object, for instance. Or you have some other sharpening effect here, or some blurring effects that can happen in the last images. So the concept of filters is not something that is new, that has been introducing through the convolutions and the convolution neural network. Is something that has been studied for decades, that has been handcrafted and used in a machine learning framework where the features were handcrafted. and then classified with like some machine learning techniques, random forest or SVM, for instance. And now the CNN is a way to also learn those filters. So eventually, what I'm going to learn with my filters is exactly one of those filters. But I'm not restricted myself in learning those filters and those intermediate representations. I can learn something more abstract, like the concept of wheel or wing or engine, for instance, on an image, or an eye here, for instance. So how does that work in practice for the filters? So whenever you have filter vectors with RGB colors, for instance, you have a kernel, which is the parameters that has the value of your convolutional, the 3x3 set of weights, basically, that you can either learn or hand make for each of the RGB channels, and you basically just convolve that operations and extract the value by summing that. Again, if you realize what that is, that's a linear combinations of the RGB for the neighboring pixels. So if I take that output here, minus 25, it's very small, so if you can't see it, it's actually the linear combination of the values of the RGB image here, multiplied by some weights that are minus 1, 1 for the neighboring pixels, for the red, the green, the blue, that are added together and create some value in the intermediate representation. There is some concept that is quite important in convolutional neural network. For instance, the padding. What happened to the borders? What happens when you actually have missing informations? There is like a concept of padding. You can drop the part of the images where the filter do not fit simply, and only keep the valid input. But it means that if your filter is a 3x3 and your image is a 4x4, like you can actually see the blue one here, you will have an image that will be a bit shorter on the border. That's something that is called like the valid padding. But you also have something called the zero padding. If you want to keep the same structure and the same size of the image from one layer to the next layer, you would just artificially create a larger image with empty values set to 0, because the linear combination of something that is multiplied by 0 is actually 0. It does not have any contributions into the next layer. And that's a way to conserve the dimension from a layer to the next layer. You also have the concept of stride. A stride is sometimes I have too much information. Sometimes I have a very high resolution image, and the stride that I'm actually using, which is the distance I'm actually taking those steps, yeah, is basically larger, such that I have a smaller image. And sometimes that's something that is desired, because sometimes I have very highly resolution images, but I don't want to actually take all those informations, and I want to downsample the output. And then the different activations is like very similar to what we had before for the linear, for the neural network that we had before. Any previous activation actually fits in convolutional neural network. If this is my linear combination I just told you, if I have a transfer function, which is a max pool, which basically takes whatever is negative and force that to be 0, I'm just putting this value and I force them to 0. And by doing a lot of linear, ReLU, linear, ReLU, linear, ReLU, linear, I can actually create some regions. So if you look at that from a top view perspective, if you want to classify the red region with the green region, you can see that you can actually create a circle or like a polygon here that will be classified as green and this one as red. So you can understand that dimension as the likelihood of specific pixels to belong to a specific category. And you can play with the parameters for them to shape and look like what you expected in a fully supervised fashion. The pooling layers is also one model blocks. You can have like a max pooling, min pooling, sum pooling. Basically, the scope is to reduce the resolution. If I have an image that looks like this, or an intermediate representation that looks like this, if I do a max pooling of a 2x2 filter and a stride of 2, it will take the maximum value of those values and just put them here. It's a way to reduce the resolution of some information without necessarily losing the spatial information of that specific patch. Those are different layers that has been, different module, different blocks that has been built over the last years that has been combined together to create larger convolutional neural network and allow the boom these days. Another concept that is quite interesting as well is the concept of dropout in training. Basically, if you want to add some redundancy to the network, which is often the case when you use CNNs, dropouts is basically, I'm going to drop some of the neurons and I will just not use them randomly for specific layers, just to create a redundancy in what I'm actually learning. Imagine if you have a layer with 1,000 neurons, you maybe not need 1,000 neurons. So you actually drop half of them and try to learn only with 500, but you will drop them like randomly. If you drop them randomly, iteration after iteration, you're kind of like duplicating the information of the neurons, which will be even more performance when you actually run the testing time, where you run in a fully, with all the weights you have learned so far. So those are like I went a bit quick on the different blocks of the convolutional neural network, and they're actually used in many different architectures that Anthony is gonna present now for the convolutional neural networks that have been sequential in the past.
Now basically we've seen most of the building blocks that are used in a lot of architectures, and actually this is all we need basically to understand everything that we're going to present now, which are actual architectures that have been proposed in research, actual works that are doing segmentation, that are doing different tasks. But before we move to that, do we have questions online or in the audience here on the CNN convolutional neural network part?
Might have been a bit fast, so feel free to reach out.
Yeah. So the idea of the CNN is really like to learn a neuron, but you're going to just travel across your image. Right? Just
this is really questions from the online.
Okay.
But we have a question. I heard the term of pruning. Is it the same that
dropout? No, pruning is a bit different. So the scope is the same. Pruning is used when you want to deploy your neural network into somewhere where you have less compute power. So typically, some networks can actually be put on the phone, but if this is like too heavy, there is maybe millions of parameters and a lot of operations, it's actually very time-consuming, and it takes a lot of time to actually to process an image. And on a phone, you basically have a small compute power. You don't have a GPU, for instance. So you want to process your image in a fast way. What you can do in the pruning, and so-called, sometimes you also have the same concept with quantizations. You want to take your weights that you have learned and drop some of them in testing. So when you actually have trained fully, basically it's inverting those two images. You're basically training with a fully connected neural network, and then you would identify which neurons are kind of useless, do not provide much information. You will remove them and make the operations a bit lighter now. And because they are lighter, they can actually run faster, and you can run faster maybe on the phone, for instance. So there are like some research is completely transversal to what we're actually explaining. You can work on any neural networks you can think about. It's just a way to either dropping some neurons at the deployment time, or quantizing some of those values to save memory. Typically, if every single arrow here is float 32, which means that it uses 32 bits to be represented, you can simplify that values to only 16 bits or 8 bits. That won't change that much. It might be rounded a bit. So instead of being, I don't know, factor of 2056, it might be actually rounded to 2055. It does not change that much, but in terms of space, you can reduce by a factor of 2 or a factor of 4 the space needed to allocate in your model, and the operations can be done faster. That's the scope of pruning, reducing neurons, and quantizations, which is simplifying the way you actually store the weights in your model. Yeah.
Thanks. And so, yeah, typically this is like the general structure of a convolutional neural network. So like Silvio said, a bunch of convolution layers first, activated by ReLU, for instance, and then max pool to reduce the dimension. And the idea is really to reduce the dimension step by step by applying those convolutional neural networks, building some abstract representation of the image, and up to a point where the image is small enough to be put into a dense neural network, so like the linear layers that Silvia was showing with the neurons. And typically, like here, if we have a look, so let's imagine we have this 227 by 227 image. If my first convolution layer is a 3 by 3, so by 3 kernel, because I have 3 channels, then this means that I can analyze a first path on all of my image with just 10 parameters. With just 28, sorry, parameters. So 9 by channel plus 1 bias term. Instead of having to do it with 227 times 227 times 3 times the number of output neurons that I want to have. So it's a much more efficient way to analyze those images. And then still for the boundary, finding the boundary between cats and dogs and stuff like that, we use regular neural networks as introduced before, but once the dimension unity is small enough. Now, if we take a look actually at what happens at those different stages, we can see that in the initial modules, what is actually captured by those feature maps, and this is what was Silvio was showing before, like on the whole, like on the image on the internet with all the gray images and stuff that we're showing, is that the first convolution, what they are going to capture is usually some very low level features such as edges, corners, and stuff like that. So just like computer vision filters would do, but these are automatically learned. So whether they are useful or not is up to the network to decide on those values. Then in the middle, so let's say around the third or the fourth block, it's actually mid-level features. So assembling together edges and corners to represent, for instance, that if I have 4 edges with the angles of 90 degrees, it means that I have a rectangle. And so this is what is going to be represented in those layers. It's also textures that are going to be highlighted in those layers. And all of this information is actually going to be used in the last modules to be assembled together and to have more like semantic features. So like this is a face, this is an eye, this is an ear, and so on. But we're not enforcing any of those. This is just something that researchers have figured out, and actually I think it was Google with the Deep Dream work that showed basically those how those features represent different stuff going back into the network. But these are not learned. It's just something that happens, not something that is enforced actually. So let's have a look maybe at some of the typical architectures that were proposed over the years. So we can see that it started with AlexNet, which was the first convolutional neural networks back in 2012, 2013, if I recall correctly, or maybe a bit before. Yeah. And then moving on towards all other architectures that were proposed. And every time the idea is to go deeper in the network, so introducing more parameters to improve the performance, changing the architecture such that there is no problem with convergence during training and so on. Because the deeper your neural network is, the more it is prone to divergence or underfitting or all these problems that you may have during training, because simply the loss, the search space becomes much larger, and so it's more difficult to navigate during optimization into this space. So let us just reshare the slides. There might be an issue.
All good.
All good. We're back on track. All right. So let's have a look at a few of these architectures first. These you will probably not use, hopefully not, because they are a bit old at the moment. But here is an example of LeNet 5 that was proposed by Yann Lequin in, I don't have the 1998. And so here it's simply like some convolution networks, convolution layers, so convolution pooling, and then directly dense network, even layer, and then the output. So very simple, very few parameters, worked well. Then we got AlexNet that made the first very big jump in terms of improvement of performance. That is also still the same kind of architecture. So we have different blocks that are doing some convolution, pooling to reduce, going a bit deeper, and then some dense layer at the end. So very similar architecture.
I might add something. It's not a problem of the image here, but basically the reason why it's truncated is because that many parameters couldn't fit in a GPU back in the days. So the way it actually been trained is by only putting 1.5 neural network and then alternating between the two. So actually the reason it's truncated the image is because back in the days we didn't have powerful GPU enough in 2012, but we were still able with Alex Karpati, no, Alex. Got so many names. Krizewski was able to actually train this AlexNet model.
Then there was this VGG architecture, still following the same kind of convolution activation pooling, but going deeper in the layers. So you can see we went from just 7 layers to 16 layers. This VGG was actually used a lot also in different fields like medicine, to analyze medical images, to analyze also sound spectrum and stuff like that. And it's a common architecture, a bit outdated nowadays, but still it was a big part of research for some time. Then moving on towards even deeper architectures, GoogleNet, 22 layers. I'm not going to go towards exactly what it is doing, because it's exactly the same modules that are used. It's just that they are going deeper, 22 layers, and going, so yeah, from 138 million parameters for VGG to 4 million parameters here. And so it's really like all the networks. What's important to understand here is that all the networks grew with also the growing of the GPU industry. So every year, new better GPU comes out, so we are able to fit a bigger network inside, and the performance increase. And this is what happened during that period between 2029 towards 2014, is that better GPUs were available, and so we were able to go deeper into the networks. But at some point, there was an issue that we're going to look afterwards, is that going deeper was not performing better, just because it was becoming impossible to train deeper and deeper networks, but we're going to look at that a bit after. And so if nowadays, we are a bit better separating these different modules. So if I take, for instance, this part here, we can see that we have first a convolution part that is going from the input image towards around here. And then we have this fully connected part that is taking the decision boundary. And so the way we are now referring to these different parts is that we have, so our image is going into what is called an encoder, and you will hear this term a lot. The idea of the encoder is to go from the high dimensionality of the image space toward the compact feature representation in some smaller feature space. So going, for instance, from 6 million parameters towards 512 compact features representing the content of the image. And there have been many encoders, and we're going to go through some of them right now. And so these features are then put into what is called a head or a decoder. And the idea of this head or decoder is to take the features, the compact features, and to transform them into the desired outputs. So whether it is the class of the image, the bounding boxes, the segmentation mask, some text, if we're doing text generation, whatever. But like nowadays, you can think of a model into these different modules, especially for computer vision. You really separate the encoder part from the decoder. And what is interesting, well, like what is the heaviest part to train in those model is usually the encoder part. Why? Because it is the part that is going from the high dimensionality towards the low dimensionality. Because this is really the part that requires the most data to train. Because to build a strong feature representation, you need lots of data, and you might need lots of annotation depending if you're doing supervised learning as well. And so one idea is to use pre-trained encoders. So you may have heard of, all right, I'm taking an encoder that was trained on ImageNet and I'm adapting it towards, or fine-tuning it towards my application, so whether it is satellite images and so on. And so the idea here is really to leverage large-scale data sets, such as ImageNet, for instance, train an encoder, and then everyone will reuse that encoder with the weights that are trained on ImageNet and just fine-tune them for their application. So this means that you can then fine-tune the model on much less data, because it has already learned some interesting feature representation from the very large-scale data set. Some of the works are also just frozen the features. So frozen the features means that we don't optimize them anymore. So we are taking an encoder that has been trained on previous data, and we're just fine-tuning the head or decoder part. And this can be done on much smaller data sets and so on, which may be available, like large-scale data set may not be available in every possible application. And so let's have a look at a few of these pre-trained encoders that are typically used. And the first one is the residual neural network, ResNet. That was actually the first very deep neural network. So when training a neural network, if you remember, you need to update each parameter of the model based on the derivative of the loss. And so one part that we skipped in this presentation, because otherwise we would have gone too deep into the mathematics, is that actually we're doing step by step. So we're doing it from the output, then changing all the parameters of the last layer, so the one in blue right there. And then we are going back, we are going back one step at a time and updating those models by propagating the gradient using the chain rule of derivative. So I'm not going into the mathematics here, it's just the idea. One thing that can happen is that this gradient becomes smaller and smaller when going back, because it's always multiplied by some factor that is below 1. And so what happens is that you have very, very low guiding signal at some point, so going back in time. You may have some very low signal to train those parameters. And so actually the first layers here don't receive any signal, for instance. And so one way that ResNet solved this is by using like these skip connections between the different blocks. So every block here represents a 3x3 convolution that can be activated. And so these skip connections actually allow the gradient to flow without being damped towards the beginning of the networks, and this allowed to really train very deep neural networks. And so this ResNet network is usually trained on ImageNet, for instance, and then reused as is for other type of application, even for analyzing histology images or satellite images, because it learned some interesting feature representation. And the way we do that is we simply skip the last part, so the last layer here, which is the fully connected layer, so the neural parts that actually maps the feature representation to the output. We just skip that, and we take the feature representation, for instance, at this stage right there, and use that as input for our edit or different type of application. So this is very commonly used, and there are several versions of ResNet. So ones with low number of parameters, ResNet 18, for instance, and one with larger ones like ResNet 50 or ResNet 101 that you may have heard about. The difference between these are just the number of layers that are there. Now, this is more advanced. I'm not going to go into the mathematics again because this is not the scope is not really the mathematics here, but really more understand the logic behind. It's called vision transformers, which were proposed a few years ago, and that really make a big jump between convolution networks and then vision transformers. And actually, this transformer architecture comes from the natural language processing and was adapted to vision and really improved the performance. So what is the idea here is that when you're using a convolution, like Silvia said, what you're doing is that you're aggregating information that is very spatial and very close to each other, right? But what if to understand the image, you actually need to mix information between different parts of the image that are not close one to another? Then what you can do is use a neural network, like dense neural networks, but then again, the number of parameters completely explodes. So here it's a bit in between the two. So the idea is still to divide the image into different patches that can be overlapping or not. They are not in this case. To project each of them with one neural network, small neural network, so like a linear projection that you can learn, and then to mix the information between these different representations directly. So you will maybe have the first patch that is going to be represented by, let's say, 16 values, the second patch by another 16 values, and so on. And then you're going to do what is called attention between those different patches. So every patch information is going to be mixed up with every other patch information in a kind of 2x2 matrix. A 2x2 kind of style matrix. And the output of this can then mix information between every patch with every other patch and every patch with himself as well. And so then on top of that, you'll get some features that can be used for classification tasks, and you just need to use head on top of those features right there. Now, these models are very heavy to train, so you need lots and lots of data, which is why usually they are trained on very large-scale data sets, and then we reuse them, the weights that were learned on those huge data sets, and just learn a new head that just depends on whatever we are using as we are interested in as a task. But they are very good for mixing spatial information that comes from different regions. Now the last one is if we want to mix information that is in the image space with the text space. So you've most probably seen a lot of promptable tasks where you specify with text what you want for the output, and that will, for instance, let's say I want to segment the puppy on the grass there, and I want to input that as text, and the network needs to know that it needs to draw a mask around just the dog that is there. To do that, you need to have a common language between the text and the images. At the inputs, they are very different. The text is represented maybe by ASCII characters, so on 8 bits per character, and the image is RGB plus however number of channels we have. And so to do that, what we're going to do is we're going to learn a text encoder and an image encoder that will try to map similar semantics toward a common space that you can think about as if it was a common language between the two. So translating this text into a language that is common between images and text. That is very abstract. We don't know what those are, right? But we want to have something that if it shows this puppy on the grass or tells with text puppy on the grass, that it will converge when we go with the text encoder and the visual encoders towards a similar number, a feature vector that is similar. And this is done using contrastive learning. So I think there was a question about contrastive learning earlier. So what we're going to do is that we're going to encode all the different texts that are in our data set, all the different images that are in our data set. So you can see T1 and V1, for instance, here. And what we're going to do is that if the text corresponds to the image, so this has been annotated, it's labeled that this is an image of a puppy on the grass. We want both representations to come closer together. And if it is a text that doesn't have anything to do with the image, so let's say the text was saying here an aerial view of a building, then we want the features to be very separate one from the other. And so by learning that, so CLIP is able actually to create this common language between the two. So this means that whether I input text or images, the output that I will get will be semantically relevant in the same way than the text and the image. And this is used in a lot of architectures, just like we're going to see after the next break. So now let me just go a bit quickly over the other learning paradigms that we've seen today. So here we focused for all the different parts on this supervised learning approach. So we have data and we have label that corresponds to whatever we want for the task for every of them. Then we have semi-supervised, weakly supervised, and self-supervised. So let's jump into the semi-supervised learning task. So here, the idea is that we have a very large unannotated data set, and we just have budget to annotate part of it. So let's say you have images from all around the globe, and you know that you only have money to annotate a part of Europe, for instance. How can you leverage during training all the other parts of the world by not having to annotate them? And one very easy, this is the most simple method that you can do, is that you can train. So here you have your label data set, right? You have, let's say, each point represents an image, and the color represents whether it is the class 1 or class 2. You can train a machine learning or deep learning model on those images, and then you can do inference on the remaining images that were not annotated. What you're going to end up with is some predictions for each of those data points that were not annotated, and you can consider them as pseudo labels. So like labels that are not manually annotated, they may contain mistake, but still that maybe the model can use. And then what you're going to do is that you're going to retrain a model on both this small manually annotated data plus all the predictions that you did with your model. And actually, you are able to do that iteratively. So I can train a first model on this big data set, but now the model that I have is actually better than the model I used before to do the prediction on those data, hopefully. And so you can re-predict on those unlabeled data right there with the new model that you trained on all the data, and it will produce a new set of pseudo labels, with hopefully corrected errors, and you can train a new model on that. And you can do that iteratively up until some saturation of the performance. Because of course, you're never going to reach out, or it's very rare that you reach out the same performance as if all of this was manually, properly cleaned, annotated data. But still, it allows you to leverage a large amount of unlabeled data still in this sense, which is very interesting. And another part of semi-supervised, if you include human in the loop, so you could include, for instance, someone to check a few of those annotations, is the field of active learning. And I have a slide on that. So here the idea is exactly the same. I start with a labeled set of training data. I train a machine learning or deep learning model on it. I apply the predictions on my unlabeled pool of data. And then I'm going to ask an annotator to annotate part of this data. Now, if you do that randomly, so you just sample, let's say, 100 images and you ask someone to check them, it may not be very efficient. Why is that? Simply because maybe the data that you are annotating is already very similar to the labeled data that was in my training set. And so the goal of active learning is actually to find what are the best data to annotate. So you can rely on some uncertainty measure like entropy and stuff like that, where the model is really unsure to select the most relevant data, or you can do some statistical analysis of your data, so checking if the data is similar to the one in the training set. There are tons of strategies that you can use for that, but it can really reduce the burden of annotating data. But this also requires a human in the loop, so also some resources to put on the table. So this is for semi-supervised and active learning. Now moving on to the weakly supervised part. So let's say that I want to have a task that is segmentation of different objects. So here, for instance, the dog that is on the lap of the kid in the image, but I don't want to annotate the mask. what I can do is just tell the network, all right, I have an Australian Terrier here, so it's a kind of dog in the image, but I'm not telling you where. And by building some specific architectures for that, so I'm not going to go too much into the details here, but it's using the abstract representation inside the network, you can actually see which region activated to classify this image as a dog. And hopefully, the regions that activated are the ones that correspond to the object of interest, of course. So here, the Australian Terrier part. There are some much newer techniques than this class activation map, but know that this is also something that can be used if having the labels, the real labels that I want to get at the end is too expensive. I can also work with sometimes with easier to get labels. So for instance, just one label per image rather than all the segmentation masks. And finally, in the self-supervised learning part, here we don't have labels at all. We just have images. And so here the idea is really to learn a good encoder. So a good feature representation for our images. Here I'm showing one of the most recent work on this self-supervised learning, which is called masked autoencoder, and it is used in this segment anything network model proposed by Meta that we're going to cover afterwards. So, but here the idea is that I have a bunch of images and I want to learn all the object representations that are inside those images, but without having explicit labels on them. So what I'm going to do is that I'm going to start from a target image. So let's say this flamingo picture right here. I'm going to divide the image into patches and I'm going to mask out some of the pixel. So this is why it's called masked in the masked autoencoder. So I'm going to mask out by putting, for instance, 0 values, or here 127, and I'm going to use the information from the visible patches right there to try to reconstruct the whole image of flamingo. So what does this mean? It means that the encoder will need to, from the visible patches that are there, find a relevant representation that says this is a flamingo, or this is something. It doesn't know what a flamingo is, but to represent the overall object, because then the decoder part right there will have, from this sparse information of the feature space, try to reconstruct the whole flamingo image. And so then once the training is done, so you do that for tons and tons of images, so this is like days of training on tens or hundreds of GPUs. It really takes a lot of time. But what you get at the end is a good feature representation here that even works with sparsely available data. And then when you put some new image in there, it will produce a feature space right there that will be very relevant to the image that is shown. And actually, so what people have done after that is that they just take this feature representation, they train one single projection layer, so linear layer towards an output for a classification task, and they show better performances than what was done before training end-to-end the whole network. So this means that it allows to really build a very strong object representation. And there have been subsequent works on video representation, or using motion to actually encode better some data in video streams. But yeah, basically these are some learning paradigms that are useful and that are going to be useful for what we're going to see next, so in the computer vision for Earth observation points. So first, before we dive into this, do we have any question on the chat or here in the room? What we've seen?
Not online.
Not online?
Not online.
Good. All right. So if we're good, we can continue. Okay for you? Yeah. Perfect. So let's have a bit of a look at some more recent works that have been done for Earth observation, and I'm going to build up first towards the GeoSAM work. So starting with the original work of the segment anything network model from Meta. So I don't know, here in the room, who has heard about this segment anything model by a raise of hand? Maybe?
Heard.
All right, so almost everyone. That's good. So here the idea is that you will have an image and the model should be able to segment any of the object inside. That's the first basic idea. So the segment anything part. Now in this particular work, what they are also proposing is a good interface that you can try out online. So if you put segment anything model from Meta, you can test it. And so what you can do is that you can prompt the model with some specific request to actually segment objects of interest just for you. So for instance, here we can see that the user is trying to segment, for instance, first the fish by clicking a single point on it, and then the model is able to segment the whole fish. You can prompt it also with text, so you can input some text, say I want to segment the blue fish on the right, and the model should be able to segment the blue fish on the right. This is the promise. Also with bounding boxes, and the last type is with some rough masks. So there are 4 ways to prompt that model. So this segment anything model is said to be a foundation model for semantic segmentation in images. And what is a foundation model? Because you may have heard of this term foundation model. What does it actually mean? So we talk about foundation model here when we're talking about a model that was trained on a very large data set that ranges from very different data distribution. So it should cover, a bit like Silvio was saying before, the whole world, basically. Trying to learn every possible image distribution that the model could have, so on very extra large data sets. So this is what we're talking about. And the advantage of foundation model is that they can be applied across different use cases in what we call zero shot. And this zero shot may be a very fancy word, but what it actually means is simply that you don't need to retrain it on your task-specific data. So like we said before, usually people use pre-trained encoders and then they fine-tune the head on their specific task. The goal of foundation model is that you can apply it without retraining this head part. You can apply zero shot on new tasks without having to retrain it on specific data. And so this is the promise of SAM. Of course, there are some limitations that we're going to discuss, but still it's a very good model for all natural images, for segmenting all natural images. And I'm going to try to demystify a bit what is behind, so how it is built, and to show you that this is a really good engineering work, but it actually relies on every module that we've seen before during this talk. So first, so SAM was trained on what they call the promptable segmentation task. So this means that the input is not only the image, but also some prompts that can have different values. So first, the image right there is actually encoded into an image encoder. What do they use as image encoder? Well, actually, they are using a VIT model, this vanilla, so one that was available in the literature, that is trained using masked autoencoders. So basically, they took something that was from the literature already available, a vision transformer trained on self-supervised data with this masking strategy. This is the encoder part of SAM. Now for the prompt. So the prompt can have different representations, so either point. So let's imagine that I just point to the middle part of the dock right there, a box. So if I draw a box around the dock, something like this, a mask. So let's say that I use a brush tool to roughly say I'm interested into this part of the image, or a text. I say I want you to segment the dock. And this is done through a prompt encoder. The prompt encoder is very simple because the dimensionality of the prompt is already very small. So if it's a point or a box, they simply do dense layers and or very small attention in there. So it's just like Silvio was showing, the neurons, basically neurons encoding the XY values. Thank you. And if it's text, what they are using is the clip encoder that was linking the similar language between text and image. So it's very simple. And everything was available in the literature. And then what they do is that they train a lightweight mask decoder. So this lightweight mask decoder is also a vision transformer, so like the one used in the image encoder, but it's a bit smaller. Because it's already working on feature representation that have smaller dimensionality. But it's still the same, and they are training it on annotated data. So they have some mask associated to the image and the prompt. So they already had this dog segmented out by a human, for instance, in some data set. And then the training is done end-to-end. So this means that the lightweight decoder is trained, the image encoder is trained, and the prompt encoder is trained. Right? So I'm skipping a bit some very technical details, but the idea is there. It's using the building blocks that we've seen so far. And then they have some very good training strategies because you have to fine-tune a big encoder model, you have to fine-tune the decoder, you have to fine-tune the prompt, you have to make sure that the training goes well and that the loss decreases, and there's a lot of very good engineering in this work to actually do that. Now there are some ambiguities also that they discuss it in the paper, is that, okay, if I click, for instance, on the head of the dog in my prompt, right there, so I click in the eye part, do I want to segment the whole dog, only the eye, or the head of the dog? There are some ambiguities. The way they deal with that is actually very simple. Instead of predicting one single mask, they will predict some 3 or 4 masks at the end that represent different scales of around the point that was annotated. So they maybe do a mask on the first part, on the head, and on the whole dog, and then they will use the loss function only on the mask that was closest to the prediction. And that's so. This is one way they did it. Now, when you are using it during inference, what you can do is specify positive points and negative points. So saying this is the object I'm interested in and not this, and this can help you really identify all the different lines. Now, why is SAM working so well? It's not because of this architecture. This architecture has been in the literature for a lot of time. Now they introduced this prompting part, which was new in the paper. But what is really the reason is the data set that they train it on. So they train it on a very, very large data set. So I think it is 1 billion masks of different objects, which is like the largest data set available for semantic segmentation. Now you may wonder if they annotated all of that manually, and the answer is no. Actually, what they do is they started, so they created the dataset in 3 steps. They started with assisted manual step, which is basically manually annotating the images and correcting them. So a model predicts some mask and they correct it manually. So this takes a lot of time. They are doing it for, I don't remember exactly how many images, but they are doing this first step, and then they are training a network on this new manually corrected dataset. Then they do a second step where now they call the model SAM. So they have trained the first version of SAM, which is trained on some data, and they are doing also semi-automatic, but with the model that they have. And so this is actually semi-supervised learning, if you remember. They have a SAM model, they have a few annotated data set, a few annotated samples, and they have a large pool of images that they want to annotate next. And what they are going to do is still, in an active learning way, retrain the model on specific images that they are going to do it as a step. So here it's really the SAM model being used in some kind of semi-supervised or even active learning part, because there is still human in the loop. And the last part is actually fully automatic. And so here they are really doing the semi-supervised, as we've seen, just applying the SAM at this train at this stage on much more data. So you can see here 99.1% of this 1 billion masks is actually fully automatically annotated by the SAM model, and then they retrain the model on this new very, very large data set. And so this is why they claim to achieve, of course, the largest semantic segmentation data set, simply because like 99.1% of it was annotated manually, automatically by the model, actually, in a semi-supervised fashion. So yeah, this is really like why SAM is working so well, because of the huge amount of data that it was trained on. Now, there are some limitations that they discuss in the paper, so this is not me just saying that their model is bad or something. I really like the model, and I think it's great for most natural images. But here in the paper, they discuss that actually it is very bad at finding fine structures. So it's good at finding big objects and so on, but not fine structures. So, for instance, here the roads would be very difficult to predict by SAM. The model also hallucinates sometimes. So this is what they report. So it can see things where they are not. So if you prompt it with some text like here, if I say, show me the dog, maybe it will highlight some of the houses. So it can hallucinate sometimes. They also say that the model does not have that much crisp boundaries. So this means that, for instance, the houses will not be perfectly delimited to the pixel, but it's more like a blob around what is supposed to be a house. Now, if you use the model that is available online, it seems very fast, because when you click on the different parts, it automatically updates the segmentation mask, or if you prompt it as well. But this is because the encoder part is already processed. So they take, when you load the image, before you make the first prompt, they already compute the features that are going to be used. And so if you actually have to do it like for different images, it's going to take every time a lot of time to recompute this feature embedding actually. So it's not really time. It's really time once you have the feature representation. It's not really time otherwise. So if you have to do everything from scratch on different images, it may take a lot of time. But it's still a very good annotation tool. And again, so SAM was trained is supposed to be a foundation model, but still the data set that they use is finite, as everything in this world, right? And so this means that if you give it images that it has never seen before during training, there's a possibility that it will not work well. And so this could be the case for some remote sensing. If you're using, let's say you're launching a new satellite with new bands that you want to analyze, or in the hyperspectral part with new bands that are available. If SAM has never seen those bands before, you cannot expect it to have good performance on those bands if they are very different in terms of structure from what was in the data set. So these are, of course, limitations. Now, a bit more recently, there was the SAM v2, so still by the same authors, more or less as the SAM v1. And here the idea was a simple extension of SAM from images to videos. And so the way this is done is that, so they retake all the different parts of the segment anything model that you can see right there. So this is exactly the same. So before, the image encoder and the prompt encoder were directly connected to the decoder. And now what they do is that, since they want to include some videos, is that you're going to do the prompt in the first image. It's going to produce a mask using SAM, regular SAM. So if you use SAM v2 on images, it's exactly the same as SAM. They just changed the encoder part with another model that was working a bit better, but that's just a detail. And then what they're going to do for the next image is that they're going to build a memory bank of the previous annotations that was done. So this memory bank contains information that is coming from the segmentation mask that was outputted in the first frame, and from the image encoder here. So some high-level representation of the features that are there. So probably features that say that it is a dog running on the grass. And they are going to update first in, first out queue of those features, and then do some attention between the memory, so the memory bank, and the image encoder. So this means that information is passed on from the previous segmentation mask that was done in frame 1 towards what it needs to do in frame 2. So this means that you don't have to re-click on the dog in every frame to say, I want the dog, I want the dog, I want the dog. Through the memory, it actually understands that this is what you want up until the end of the video. Now, there are also some limitations here because the memory bank is a first in, first out queue. So this means that if the dog is not visible for a certain amount of time and the memory is finite, then it will have forgotten what it was looking for. And so you will have to re-click on it. Now, they're also included here, which is a very good feature, I think, the option to prompt it also at some subsequent frames if you think that it drifted away from the original image. So you can recorrect and it will reinitialize the mask at this point and re-update the memory bank for the subsequent one. So it's a very good tool actually to annotate images in videos because it's much faster basically. And now moving on to GeoSam. So now there are a few papers, not papers, but works that claim to be GeoSam. So everyone now is...
Maybe just a question before to move to GeoSam. Between SAM and SAM2, the only difference is this video and the memory that you have, or nothing else?
No, the rest is very similar. It's just that they changed the image encoder from VIT to another model called Yara, which is a hierarchical. But I mean, the goal is still to go from high dimension to low dimension.
Okay.
A better model was released in between, and they just used that.
But I'm asking because I had the illusion, at least, that the segmentation was slightly better. So the border of the object was maybe more accurate. But
it could be slightly better because of, so if you use it on image, because they changed this encoder part.
Okay.
So it could be slightly better, but if you use it image-wise, they say in the paper that using SAMV2 on an image is the same as using SAM on an image, just like, yeah.
Okay, interesting. Yeah.
Exactly. And so for GeoSam, so right now everyone is a bit trying to have his own foundation model for whatever task on his own domain-specific data. So GeoSam is one of them. There is also MediSam for medical imaging and so on in different. And so here what they want to do is to fine-tune the SAM model for specific data distributions. So here, for instance, satellites or aerial data. So you don't be confused because there are a few words that are called GeoSam, geo with a dash, geo in one word. So this what I'm presenting is the one that has a scientific paper attached to it. There is also some code called geo-sam, but I didn't find the paper, so I was not able to read exactly what they do. But this is one of them, and it really represents well the idea that I want to pass on anyway, which is how to fine-tune the SAM model towards a specific data distribution that was maybe not very well understood by SAM. And actually, what their starting point is that they try to do SAM for crosswalks and sidewalk. Yeah, walkway. Exactly. Thank you. And they noticed that it's a fine structure, and so SAM doesn't work well, like they claimed in their original paper already. So what they are going to do is to fine-tune this SAM model, V1, on this specific data. Now, unfortunately, they did not have a good model, a good data set to train that model. So they did not have an annotated data set for that. So what they relied on, they don't specify it in these terms in the paper, but this is something that the community refers to as a distillation. So what they are going to do is to leverage another model that is called Tile2Net. Maybe you know it. It's classifying satellite images into 4 classes, including walk path and crosswalk. And what they're going to do is that they are going to create pseudo labels using that Tile2Net model. And then they are able to retrain SAM. Now, of course, training SAM was a very heavy process. Not everyone is meta and able to put a million into training models. So what they're going to do is just fine-tune the decoder part. So they still use the same encoder and they freeze the parameter, so they don't have to do optimization on that, and they freeze the prompt encoder part as well because it's heavy to train. So they are just fine-tuning the lightweight decoder on those parts. And what they are showing basically in the paper is that they are improving the performance compared to SAM. Now, I have some maybe doubts about is it better than Tile2Net or not. I'm not sure. It could be because the image encoder of SAM is probably better than the one of Tile2Net. But still, when you're learning from an input of another model, it's hard to pass over that performance. So they were showing better results for some data sets, but not on all data sets. They were not showing the results. So this is why maybe it works better, maybe it doesn't. I cannot say 100% sure that it does. But still, they are able now to use this promptable part of SAM instead of Tile2Net that was not able to do it. So yeah, basically that's one way to fine-tune those kind of models on geospatial data, for instance. So now I've covered a bit the segment anything part. Do we have any question on that before Silvio moves to the other?
No, there was a question from Quentin, but you just answered.
Okay.
But he has another question. Quentin said, based on, do you think it might be better to fine-tune the Tile2Net rather than SAM?
The objective is different. If you want to use the promptable part or not, this will decide. But it's a good question still. Is Tile2Net, so this means that we would have access to manual annotations on geospatial data, which you may have here in JRC. But yeah, this I cannot say, it's experimental. Is Tile2Net going to be better than GeoSAM fine-tune? This is a very good question. I think it's more an empirical decision. You have to try out the two. Or if you are interested in a promptable part, then yeah, go to SAM. Yeah. But that's a very good question. Yeah.
Okay. No.
Okay, good. So, Silvio, I will
More questions on SAM? Okay. We're going to talk about something slightly different. We are going to talk about FLOGA. I mentioned to you earlier this afternoon this data set called FLOGA. It's a paper from Zdraka et al. It's a data set and also a method to do semantic segmentation on wildfire. This is typically like what a deep learning project would look like for computer vision, and we're going to use that tomorrow in our hands-on. FLOGA is a dataset of burn area annotated with semantic segmentations. It contains data from Sentinel-2 and MODIS, both the images of pre and post fire. So what you can see on the top rows is the pre-fire and the post-fire of Sentinel, which I believe the burn area is actually that area here. We also have the MODIS, which is a very low resolution that has been aligned with the Sentinel, again, pre-fire and post-fire. There's a total of 326 wildfire events in Greece from 2017 to 2021, which are located in those different regions in Greece. They contain the label of the fire. So basically, typically you would like to take the data that come from either Sentinel, 2 or MODIS, maybe the post-fire or the pre-fire and post-fires, and try to estimate that label. That has been labeled manually on top of also I forgot what's land cover.
That's called a land cover.
Yes, exactly. That's the land cover for that, which represent different classes of land cover, basically. And they also contain like a water mask that is being either done automatically or manually for the specific regions, because as far as I understood, there is like some consideration that can be done on water directly. So this is like a large-scale data set. I think it weighs like 400 gigabytes in total. We're going to use it tomorrow, mostly the one from 2017, because we won't be able to train some very large models in only 4 hours. But the content that we're going to cover tomorrow could be extended to all the fires up to 2021. In this paper, FlowGas, they don't only create a data set, but they also have a deep learning model called BAM-CD that basically takes as an input the pre and the post-fire images in a specific neural network that they have created themselves. That looks very similar to an encoder-decoder. So you have the pre-image and the post-images that are convoluted with residual blocks, the residual skip connections that we have seen before. It's a convolution neural network that reduce the resolution of that image, and takes both the pre-image and the post-fire image, concatenate those information at different abstraction level, and then redecode that or other convolutional blocks that eventually gives you a mask of that fire. That's typically like a handmade. I wanted to show you that model because that's basically what a research in deep learning, when applied to Earth observation, actually envision. You have a lot of data already that is manually annotated, that is basically available, and you can engineer either an architecture or use pre-existing architecture to actually learn some functions. In that specific case, we can classify pixels, in other words, run semantic segmentation. And there is nothing fancy in terms of like training here. Is training in full supervision. So I'm not talking about SAM or about anything. And the nice thing with this BAM-CD is that in that FlowGap paper is that they compared that with a lot of different techniques to actually estimate the fire. For instance, all the indexes, the differentiable, the normalized burn ratio, the DNBR2, DNBR+, all those handmade metrics, indexes that basically performs relatively good. I would especially look at the burn pixel with the F1 score, which is one of the best score to actually look at to evaluate these tasks, because unburned pixel, well, you already reach 97%, but that's not something that is scalable. But the F1 score is actually quite scalable. And then they also compare that with the machine learning techniques, random forest, XGBoost, support vector machine, multi-layer perceptron, and actually reform like better performances. Some deep learning algorithm that already existed before, changeformer, ADHR, and they compare that with their BAM-CD, and for some reason, of course, this architecture seems on the same data set. Again, like the idea of data set is basically just you keep the data as is, and you just want to benchmark which algorithm works well. And through this table in this paper, they demonstrated that BAM-CD, their methods, is performing better in the task of localizing fire or burn area on Sentinel-2 in Greece. Does it mean it actually generalize better than indexes? Not necessarily, but at least it's performing better in their applications. They're not talking about any generalization. They're not tested that on wildfires or burnt area in other regions, but they're focusing purely on us. Tomorrow we're going to actually work on that. We're going to develop a few of those indexes manually. We're going to work on some machine learning application as well, especially the random forest, and maybe if we have time, the XGBoost, let's see. And then we're going to also implement the BAM-CD deep learning models to basically classify pixels of burn area using post and pre-fire images. Another method that I wanted to talk to you about is a paper that we actually come out of our lab. It was published last month because I thought it was like relevant also to show that there's a lot of interesting research that can be applied and it can be that can come up based on problems that you might have when annotating images, training algorithms for your specific data. And in particular, in that paper, we're trying to learn semantic segmentations. So something like this with different classes, given that as an input. But the labels we're actually supervising our learning from is actually just points. So how would you go from point annotations to learn something that would actually eventually model that would actually learn the full labeled images? And that's, of course, you can imagine that labeling the whole regions can take hours, while for a few points it's just like a few clicks that you have to do, and you can save 10 times the time of labeling, and eventually get reach some very similar performances. So the methodology that we introduced in that paper is the following. We take the input images, we extract the concept of superpixels, and the superpixel is quite interesting because what SAM is actually outputting you is kind of a concept of a superpixel. A superpixel is a region that is basically understood as having the same semantic. So when you click with SAM with the dogs, you're expecting to get the contour of the dog because it contains the same semantic information. But it has no content of boundaries, and the superpixels are usually it's more like low-level image processing that has the concept of edge detection. So whenever you have a high gradients in the image, you would actually create a boundary around this image. I will go to more details later on. But that can create some regions where you can extend points to something larger region, larger mask, that create a pseudo annotation mask that is somehow semi-supervised because half of them have not been annotated, but not semi-supervised in the sense of more images to be taken off, but more larger masks are being generated. And then you can train a typical segmentation backbone that would create your output. So two parts. First, going from images to pseudo annotations mask that can be leveraged later on in the second part to train a segmentation mask. Into more details, when you have a specific input like this, you would like to create what a superpixel looks like. The superpixel is very similar to the segmentation created by SAM, with the key here is that we don't care that much about what a dog would be a dog, but we care more about the boundaries. In semantic segmentations, the devils are actually on the edges, where actually a building stops. And one of the drawbacks of SAM was actually that they were not very good at finding the sharp boundaries around the object of interest. So creating the superpixel extraction, we would match that with our key points, and we would transform that into superpixel and pseudo annotations. Here we have extended the points that we have annotated in light gray and white, or gray and white, and in the black is all the information where we don't know much about, whether it's a background, whether it's actually a building or whatever, but we actually have that specific region that has been annotated with the points that has been extended into a region. And using these pseudo annotation masks, which are very relevant in terms of sharing the same semantic, you can go to the second part, which is here, which is basically training a model called DeepLab V3, which is a model for semantic segmentations for the task of creating a semantic segmentation. So an output segmentation that would look like this. So the strength of that method actually is that if you have very good superpixels, and I'm not sure if I've included that in the slide, but SAM does not have like sharp boundaries, so it's not a good superpixel model. It works a bit worse. But if you look at the ground truth of this is my inputs, this is the ground truth I'm looking at, the first row you have here is that if you have a fully supervised model, which basically you are using the full ground truth that is available here, you would actually lead to some segmentation that would look like this. This is like what the output of the model, and it's somehow quite close with respect to what the ground truth look like. But interestingly, with our segmentations that was only using the query point as a supervision, you actually reach some very similar performances to segment the roads, to segment the houses, or to segment the water, for instance. And that's basically one of the strengths that we had with, we're being disconnected. One of the strengths of this method. Let me share my screen again. And actually, I'm done with this, with that part. So if you have any questions, I will be very happy to take any of your questions. I have just a last slide that I would like to share with you later, if you don't mind.
So I have a question, Silvio. Basically, with the new method that you showed us,
Mhm.
if I have points of buildings, you can recreate the footprint
Yes.
of the building.
Exactly. Exactly.
When
That's
can
the
we
end.
get that?
And we have new people that
Clicking,
can
yeah,
click
clicking on
points.
Right.
How can we have that?
Okay, well, that's a code that is available online already. So we've published that last month at the ICIP, which is an international conference of image processing. So the code is online, and basically the way it works is that it does not go from point. I mean, the way of going from point to polygon is not fully working, because if you look at that specific image here, where I was looking at what the pseudo annotation looked like here, this is basically going from points to masks, and the ground truth is actually different. It's on the same example here, but basically you have something like this would be like different buildings. And those are the points you're actually clicking on it, and you actually say that's the road, that's the roads, that's the roads, that's the building, that's the building, that's I think the grass, or I forgot what the white color is about. And then you go to the pseudo annotation. So as you can see, you actually don't have the full information of what the footprint looked like. But this could be a supervisory signal to train a neural network that would then take the task of creating the segmentation that you're looking for.
The point that you provide are used only for the labeling, or they are also used as seed point to retrieve
For the labeling, for the labeling.
For the labeling.
The seed points, when you go like super pixels like this, you don't necessarily have the full extent of the footprint that you're looking for. But the extent that you have is actually highly informative about the same semantic of that point. So instead of supervising for only a single pixel, that this is the building, you actually have a larger regions that can go from 1 pixel to maybe hundreds of pixels that can be used to supervise the models to basically train, to basically extract later on the segmentation mask. So it's kind of like, I would call that weakly supervised. So it's weakly supervised in the sense that I don't tell you the whole extent of the building. I'll tell you like there is that point that I'm extending, and basically like the white region, you can see I know for sure that most of the points here are actually from the same building, for instance. So I'm using part of the labels of the footprint that I can know for sure 100% through the superpixel techniques that those points actually belong to that specific classes, and then I train them on models that can actually find very sharp edges. And yeah, the deagles are in the edges, and these superpixels are really good at those edges, way better than the SAM. So using SAM for that, using SAM instead of these superpixels will lead to worse performances actually. Any questions?
Yeah. Could go back one slide, please, to see the input image. Now, for me, the main challenge here is the shadows, because they're associated with each of the buildings and each of the trees. And if you see an image of the same location at a different time of day or season, shadows will be in a different direction. How is it performing there? Because it seems as though it is deriving these or segmenting this image based on contrast, and the contrast is going to change.
That's a really good point. So the good thing is that like if I look at the annotation points, at least I've like one of the confusion would be that the shadow actually belongs to the building, but because of those superpixels, I would annotate the whole shadow either as a road here, if I have a road here. So I would consider that whole shadow, which is a very challenging example, as telling him, hey, that's a road. So I have a supervisory signal for the whole region of the shadow, telling them, hey, look, that's a road. So it actually contains that information in the training. I'm not sure that techniques would actually work better than fully supervised learning for the shadows, and I think the shadow is like a specific issue in particular that needs to be tackled. I don't know much work. I think there is like some work, I forgot if it was from your lab, that was basically trying to learn motions of objects, and the shadow is a very difficult part that might be understood as the same object. So there is ways to basically understand what's a shadow and what's not a shadow. But that's like transversal techniques to basically cope with shadows that has nothing to do with that technique.
And then you can also take into account the temporal dimension, so you can have multiple images of the
Right.
application.
Yes, exactly. So we can actually, like in the same way we have pre and post fires, we can actually have multiple stack of multiple images in time that you can just use, and hopefully some of them do not have the same shadows. So aggregating these informations at different time of the day might lead to different
Or the years.
Yeah, or the years, for instance. But they might have different changes, right? Maybe cars are parked there.
The vegetation can be different.
Right. Right.
Okay. I have two long questions from Quentin.
Okay.
So, hold on. So the first question is, do you have experience in transfer learning and domain adaptation? Considering that we work on very different satellite data, be it in terms of spectral feature or pixel size, having one single model adapt from a foundation models appears to be complicated. A solution would be to find a common feature between different satellite sources in an unsupervised fashion, e.g. with an encoder, and then passing the feature to a segmentation model. But I would like to have your opinion on how to tackle such a problem.
Absolutely. So I think, the beginning of the question was self-supervised and domain adaptation, right? Domain adaptation and
Fine-tuning.
transfer learning. So transfer learning, absolutely. Transfer learning is what happened in GeoSam. Transfer learning means I've learned an image decoder into generic setup, and I'm transferring that learning. I'm basically just taking the weight as is, and I'm basically transferring to a different task. Transfer learning means just reusing another network that's been pre-trained. Sometimes you can freeze it, like in that case, like these little snowflakes actually mean it's frozen. By frozen, it means you don't change the weight anymore. But by transfer learning, you can also like fine-tune eventually this image encoder. Again, the reason why I haven't done that here is because the image encoder is very large, so it will take a lot of time to actually fine-tune that part. Domain adaptation.
I can take that part.
Yes, because you're the expert on that.
Yeah,
go for it. Totally.
no worry. So our lab is working actually a lot on domain adaptation. So not on what you're saying, different modality, but I will get back to the different modalities just in the next step. But first, I need to set some rule, some basics of that. So for the domain adaptation part, we have different. There actually exist different types of domain adaptation. So whether or not you have available labeled data for each of those domain or not, and whether you're talking about domain adaptation on the fly. So whether it is like I have a new image that I didn't have in my training data distribution, and I want to adapt my model towards that. So in the first part that I was mentioning, you have data, you have annotation for those different domains that you're mentioning. What we can do is to learn one specific model for each specific domain. So here in our lab, for instance, we're doing that for autonomous driving, and we're learning one model when it is rainy, one model when it is sunny, one model when it is foggy, and different weather conditions. And then we have, as a test set, a new domain that may be in between the different domains. So you may have water on the road, but a clear sky because it's just after raining. And so how do you use the output of the different models? Where do you, which model do you query? That's a kind of domain adaptation part. Another one is called online learning or test time adaptation. So in test time adaptation, what you have is that you have a model that has been trained on some data distribution. It can be several models as before or just one single model. And then during training, you have, during inference, you have new images that are coming up and the domain may shift. So they may be like the weather changes or whatever can happen. And this model, you want to adapt it without relying on the labels because you don't have them. It's inference time. So we also developed techniques for that using a similar architecture than GeoSam here. So leveraging different models to create pseudo labels on this new data and retraining the model on the fly. So that's a possibility. Now, when you have different modalities and you want to have them speak a common language, which is what I understood from your question, so tell me if I'm wrong. So you want to be able to use some kind of segmentation model that can be applied from features extracted from different modalities, and maybe one modality is not available at some point, and maybe a combination of modality may be able. And this is a whole field of research that is also very active in your laboratory. How do you cope with different modalities? How do you make them speak the same language? So like Clip was doing between text and images, you can do similar stuff between different modalities. So whether it is radar images, RGB images, hyperspectral images, and so on. And how do you cope with missing modalities? This is a very wide field of research as well. And you can look into the literature also on images and videos, and so videos and audio, for instance. It's the same kind of architecture that you will probably look into. So sometimes you have the video modality, sometimes you have the audio modality, sometimes you have some text modality that is put by the user, and sometimes one of these modality drop. How do you still have a model that can leverage all the available modalities or part of the available modalities to do some tasks? So for instance, segmentation. So it really depends on your specific setup that I don't know, but we can definitely talk about it and schedule a call together to discuss a bit your specific requirements and see if from the computer vision literature which can help you find the relevant work and relevant sources, and we can talk with Silvio. His lab is very active in that part, but rather for the video, audio, text part, rather than the multimodal in terms of satellite imaging, right?
Yep.
Yeah.
Very good. So sorry, there is a second question again from Quentin, which is regarding superpixels. From experience, this can be a double-edged sword, since the parameters are usually dependent on specific pixel sizes. Having used several techniques, including mean shift, watershed, I have always had issues with generalizing to different satellite data. Do you know of any superpixel generation techniques that is not too reliant on pixel size or spectral information?
Right, and the one we use, and I'll tell you, is called DAL-Earth. That's it. That's my short answer. DAL-Earth is something that actually generalizes very well. One of the state-of-the-art for that. And I think it comes from a paper that I haven't found here. Here, Earth superpixels. And this one is the one that generalizes better. That is the paper I would refer to for that question. But yeah, actually, there's a lot of hyperparameters. If I go to the details of that part in particular, I would say that there is a high. Basically, when you build superpixels, you can decide how many superpixels you want to work on, and that's you want to create. And so you define the size of the superpixels. So it's some hyperparameters that you have to play around with. Yes, different of the scales of how many objects you have in general. What is the zoom level that you're using for satellite images, for instance, because you want to have superpixels that are consistent in semantic rather than if you cluster them, they have like what we call the purity, which is basically a single semantic contained in the superpixel. So there is some engineering tricks there.
And so Quentin say grazie.
Prego.
And you can contact us offline by email.
Yep.
No problem, and we can discuss offline.
Okay, very good. So Quentin, yes, hope you heard that we can discuss this offline with Silvio and Anthony.
Yeah.
Good.
On that, I just like maybe last slides to present you. At Chaos, we also have built a startup that try to promote computer vision in different fields, and we recently went from microscope to satellite data as well. And so we are currently have a platform where you can annotate and upload data annotate maps from different source providers, Sentinel or other providers from Google Earth Engine or AWS Earth, that allow to annotate some data, train on the cloud some state-of-the-art algorithms, and can just deploy them. It interacts very well with QGIS. You might be familiar with QGIS. We have a plugin where we can interact with that and training like customized models. One of the success story I just want to highlight real quick. So with this company, we tried also to teach computer how to see. Basically, 3 months was the time that some of the archaeologists in Saudi Arabia were needed to annotate what they called mustatil, which are archaeological structures that are 7,000 to 8,000 years old, that apparently belongs to a very old civilization that is older than the pyramids and the Egyptians, for instance. With our algorithms, they managed to actually drop down time from 3 months to 5 hours by scanning automatically the Kingdom of Saudi Arabia. Basically, it's an easy-to-use platform where people can just annotate data and train object detections or semantic segmentation algorithms. It has a very nice user interface that works in different fields ranging from archaeology, but also agriculture, where this is a typical what field in Saudi Arabia look like for crops, like this, where you can actually detect all the things. You can deploy AI model, you can annotate data. It's a no-code platform. It interacts with QGIS, no-code, multi-scale, multi-users. And we also have like some service consultancy. We're already integrating with Neospace Group, which is a Saudi group for similar to that basically centralize all the catalogs of the satellite images in the Middle East, and some drone partners as well, Shaman and Falcon Viz, and we provide many integrations from here to there. So we have already done a lot of things with all of our partners, and we'll be happy to at some point build something together. Looking for partnerships, so very happy to support you in your development as well.
Perfect. Oh, thank you. And we reach 5:30.
Yeah,
Amazing.
perfect. Perfect time.
Thank you. Just let me check if I see some comments. No, just thank you for these very interesting presentations. I'm looking forward to the hands-on session tomorrow. Yes, so it's a good conclusion because tomorrow morning we start at 8:30, and look, there's going to be another WebEx link. That's the second one to reach us. And so all the morning will be on hands-on.
Exactly. We have like a 6-10 notebook where we're going to tackle different way of how to to manage basically the Floga data sets, how to open the data, visualize the data in Jupyter notebooks, how to train, how to extract some indexes out of this image, how to train a machine learning algorithms, how to train a deep learning algorithms, how to evaluate the performances of all these algorithms, and at the end we're going to have a hands-on also on GeoSim, interactive tools to basically take everything into hands. We can also generate a lot of GeoTIFF images that are the output of those different algorithms, whether it is index, machine learning, deep learning. We're going to use QGIS as a tool to also open this GeoTIFF. Or if you have any if you are very familiar with any GIS software, feel free to actually bring your own and import then the result of this hands-on.
Super. Thank you very much. Thanks. So thanks to all the participants online. And so we look forward to seeing you again tomorrow morning, 8:30.
Thank you.
Yeah.
Thank you.